thank you very much for coming here. So, if I make a mistake in my spoken English, please forgive me for that. So, I will talk about a very interesting topic because it involves the joint of several branches of sciences. I mean, this is a joint work with a person from the Department of Statistics and Victor Guerrero, and the other one, Francisco Estrada. He's an economist, and I'm a space physicist, so it's an interesting idea to mix our knowledge in one work. So the talk will be divided in 3 parts. In the first part, I will give you a brief review about the solar system, about the solar terrestrial problem. So in that part, I will talk about a little bit about the solar activity itself, and then I will introduce you to some of the important concepts about the terrestrial climate, and finally, I will talk about the solar terrestrial problem, that this is a very important issue. And the second part is devoted to the time series analysis. So I will talk a little bit about how to deal with the time series. And later, I will talk about our proposal based on the BART methodology. And finally, I will give you a summary and some ideas for the future work in this issue. So the first part, about the solar activity. So as you know, the sun is a star, and it has a strong activity. And the solar activity, comprises a lot of photospheric and chromospheric phenomena, such as sunspots, the image that you can see here. Prominence, like here, the prominence are also called flares, solar flares. And the CMEs, the coronal mass ejections that you have here in this picture. And besides that kind of activity, you can also refer to the solar activity to all the magnetism involved on that. So the magnetic field of the sun exhibits particular features like the scales, the magnitude of the magnetic field, the orientation, and the polarity. So for example, if you are looking at the minimum of solar activity, you can find that the magnetic field of the sun is very bipolar. So it's a very easy way to study the sun in that way. But if you look at the maximum of solar activity, the magnetic field is a completely complex structure, because you can find the bipolar magnetic field, and you also have another components that makes the solar field very hard to study. So, besides that, the magnetic field, as I told you before, the prominence, also called the flares, and the CMEs are often associated to sunspots. And other types of activity involve the appearance of magnetic field tubes, like here. And in general, it involves variations in the global magnetic field. So what about the solar variations? The solar variations are defined as the changes in the amount of radiation emitted by the sun and its spectral distribution over years to millennia. So in that picture, I'm showing you just a few of the solar cycle variation that you can measure from the sun. So for example, you can see in yellow color, you can see the irradiance in the daily values, and the red one in the annual values. The sunspot observation in blue, the solar flare index in green, and some type of emission in the radio flux in purple. So you can notice that they are clearly signatures of cycles here. So the main solar cycles that you can find here are mainly the 11 years. It is the most common cycle in the solar activity, and it's also called the sunspot cycle, because you can see and you can count the number of sunspots that you can see in the surface of the sun. The 22 years is about the magnetic field reverses every 11 years. So this is another type of measure about the solar activity. So for instance, the most important cycles in the solar activity are the 11 years and the 22 years are the most common. But you also find this kind of cycles about the 70 and 100 years. and it's called the Gleisberg cycle, but it's not pretty sure that this kind of cycle really exists. And the other ones, about, for example, 6,000 years, is a long, long time, and it's not really sure that this kind of cycle really exists in the data. So they are just proposals for that. So the important point here is that the solar variations may affect in a direct or indirect manner the Earth's climate. How? Well, I have two examples for that. So the flares and the coronal mass ejections may enhance the warming through the UV-induced chemical reactions in the high atmosphere with ozone, because as you know, the ozone is created and destroyed by the UV radiation in the high atmosphere. So this is an important thing. And besides that, the volcanic activity on Earth plus the solar variation probably is not really sure, but probably this kind of combination contributed to the climate change, especially during this time. This is a long period of time. This is called the Maunder minimum. Why? It's because in that period of time you didn't observe any sunspot on the surface of the sun. So many people think that it's because at that time the eruptions of the volcanic activity and the solar variations played an important role on that. But let me tell you that the changes in the solar brightness actually are too weak to explain the recent climate change. So because of that reason, in the 2006, people think that the relation between the solar activity and the climate is not really important as the people thought long time ago. So what about the Earth's climate? Well, we have some factors that can control the Earth's climate. For example, the volcanic eruptions, the lava plus the ash and plus the tiny particles reach the stratosphere, and that kind of particles reflect solar radiation back out to space. That implies a cooling, general cooling on Earth for about 1 to 2 years. So this is a possible implication of that. So besides that, the sun, as I told you before, especially the 11-year solar cycle, can cause a small impact on climate, but over thousands of years, changes in the way Earth orbits the sun can cause large changes in climate, but it's not confirmed at the moment. So other factors besides that can control the Earth's climate can be the greenhouse gases, the snow, the ice of the cryosphere, aerosols, and many things, and obviously the man. So in general, we can talk about the regional climate and the global climate. So the regional climate is the average weather pattern in a place over more than 30 years, including the variation in seasons. The regional climate depends on the amount of sunlight the Earth receives from the sun, the altitude, the topography, and how close is the place to the oceans. And the global climate, by contrast, is a description of the climate of a planet as a whole system, with all the regional variations average. So this global climate depends on the amount of energy received by the sun and the amount of energy that is held in the system. And this is a very important thing. So what about the solar terrestrial relationships? So this is a huge area of research, and the main question in this topic is, how is the solar activity felt on the Earth? So, as you know, the sun exerts an influence on Earth because of the sunlight, the heat, the solar wind, the flux of cosmic rays. So in these pictures, I'm just showing you this type of interaction of the solar activity and the Earth. For example, in the first one, you see the sun. This is a picture, it's not a real picture of that. So the solar wind is plasma. It's composed by particles, charged particles, and magnetic field, and they are traveling in the space. And the Earth, as you know, has a magnetic field. So when the solar wind interacts with a magnetized body as the Earth, some structure like this is formed. This structure is called the magnetosphere. And the magnetosphere, you can find several interesting things inside and outside, but it's not the topic of this talk. So just to mention, Some of the particles that they are leaving the sun can penetrate the terrestrial atmosphere. And for example, in the case of the cosmic rays, you can find in the upper atmosphere certain particles that can collide with some molecules here and form another type of particles. And this kind of interaction are called showers. And as a result of that, as a consequence of this type of interaction, you can see, for example, the auroras in the northern part of the planet. So it's because of the result of this type of interaction. So it's not as boring as you can imagine, the interaction between the solar activity and the sun, and the Earth, sorry. So as the solar terrestrial relationships influence the amount of sunlight that the Earth received, it obviously has an influence in the temperature that you register on the Earth. And the temperature is associated to the climate and to the moisture that you can measure on Earth. And finally, the temperature, the moisture, and the sunlight affects all life on Earth. So as you can see, the solar terrestrial relationships involves a lot of phenomena that they are really interesting to study. Not only the climate, because you can also, because it affects also life on Earth, you can also find some works devoted to the study of the solar activity and some kind of disease, especially heart attacks. But many people think that that kind of relation is not really true because it depends on the quality of the data and the kind of the correlation that they are getting. So just to mention that the climate is not the only thing that you can study under the solar terrestrial relationship approach. So in summary, the solar terrestrial relationships involve studies of the solar spectrum, the solar constant, and the possible statistical correlation of solar phenomena, such as sunspots, flares, and prominence, with associated terrestrial activity. Which kind of terrestrial activity? For example, ionospheric disturbances, magnetic variations, auroras, weather, climate, obviously in the long term, and variations of the components of the atmosphere, especially in the upper layers of the atmosphere. So some briefs about the solar terrestrial climate links. So before searching for any statistical relationship, the quality of the data that you are analyzing is really, really, really important. Actually, because of the existence of surface networks and weather satellite observations, you can have high density global data sets to analyze, so this is an important thing to do. But besides the data, you need to be cautious because usually you tend to reasoning in a circular way. Because, for example, sunspot observations could be affected by the atmospheric conditions because you have a lot of clouds in the upper layers of the atmosphere. You cannot observe certain types of sunspots. So that could be affecting the number of sunspots. The isotope records by climate variations and the magnetic field indices by the geomagnetic field. So you need to be careful about the variables that you are including in your model because you can fall in the circular reasoning of that. So what about the sunspots and weather? Well, this type of problem was first suggested by Galileo in 1651, so it was a long time ago. And since then, a lot of work have been done in that sense. The pros of talking about sunspots and weather is the only index, the sunspots, I mean, that has been recorded for a long time. So this is one advantage. But the cons is because you don't have sunspots observation between this period of time, the Maunder minimum. So that means that you have a gap there, so probably lost records. As I told you before, probably because of the volcanic activity on Earth at that time. So probably it's because of politics. Nobody knows what happened in that period of time. So this is a very contra about this issue. So what about the solar cycle and surface temperature? In 1826, fine and settled weather followed the decline of sunspot activity, Köppen, years later, found that the temperature in the tropics peaked around a year before the minimum sunspot activity, and then cold conditions coincide with the sunspot maximum. So you have lots of work. Besides that, statistical studies that correlate weather and climate with the solar activity have been popular for centuries, until now. And in 2003, Laut found that apparent correlations that the people are reporting between the solar activity and the terrestrial climate do not properly reflect the underlying physical data. So this is important to know that some of the correlations that the people are getting, and they are shouting that they have high correlations between certain phenomena of the solar activity and the terrestrial climate, are not really true, because they are ignoring most of them the physics of the problem. So a possible mechanism that could link the solar activity with weather can be as follows. So you have the sun is an active star, and the heating causes the upper atmosphere to expand further into space. So because of that, the increased depth of the atmosphere alters the way in which vertical planetary waves propagate around the globe. So the possible consequence of this is that this may affect a couple between the upper and lower atmosphere. And finally, a possible influence on weather processes. And because you are altering the weather processes, because in the long term you can alter the climate too. So the second part about the time series analysis. So the important thing here in this work is to look for a joint model. So as a first approach, the association between the solar and terrestrial environment parameters is found through some type of correlation, and more sophisticated techniques like the wavelength analysis tend to do that. But the problem with the wavelength analysis in this sense, they are finding periodicities that they are not really true. You cannot trust that the results that they are getting are associated to solar activity. So this is for one part. In the second part, we have that the climate models are very complicated systems when you have to compute a lot of different equations and that kind of stuff. So a few of these type of models include the solar influence. So that's why it's an interesting challenge to find a joint model, and as that's the thing that we want to do in this project. So quickly, I will explain some things about the time series exploration. So when you have a time series, you need to check for the trend like this, for the seasonality and some structural break. So why that kind of things are important to look for is because if you need to apply the bar methodology, you need to have a time series that is stationary. So that's why you need to look for these type of things before. So for example, if you have a plot like this that shows clearly a trend, my advice that you should take a box cost transformation like the thing that I'm showing here. So if you apply that kind of transformation and you don't get a good time series, you need to apply another thing, that is to take into account the possible difference of the series. So this is the first difference that you can take from the time series, and this is the second. And you need to apply another test, and they are called the unit root test. And after that, sometimes your time series can show a breakpoint. That means that you are following the time series and suddenly you observe an abrupt change. So this is a breakpoint change. So you need to look that and try to model that.
In the previous slide, when you see the trend, the temperature there, if you take that trend out, are you not taking out the climate change symbol?
No, I think that the way you can consider that is through checking. I will come back to that issue, but in the case of the temperature, you can see a breakpoint here in this time, so you can model that with a dummy variable. So you are removing the trend, but you are taking into account that change. I don't know if that makes sense, but
Yes. Yeah, you can go back to that.
yes, yes.
Just a question back on the box-to-box transform. What's lambda?
Lambda is a value that you can, if you have an idea about how kind of transformation you need, most of the people usually apply this one, just the log of the transformation. But what if, for example, in this case you have negative values, so you cannot apply the log. So many people recommend you to add a constant, but adding a constant could be risky because you can change your time series a lot. So you need to be so wise in order to find the correct way. But there are other ways to find the lambda. You can calculate by exit and error and trying to find the optimal value of lambda, which gives you the best result. So yes. So let's start with the bar methodology. The general ideas of this methodology is, first of all, please don't confuse with another bar. It sounds the same way, but it's written in a different way, because this bar is the value at risk, and you are talking about finance, and you are not applying this kind of techniques. We are talking about the bar, that means the vector autoregressive model. This is a generalization of the R models proposed by CESS. The advantage of this bar methodology is one of the most successful, easy, and flexible for the analysis of multivariate time series. And this type of methodology is extensively used in econometrics and finance. So that's why it's hard to find this kind of methodology applied to physics, for example. But the bar, sorry.
You have a very common thing called 3D VAR and 4D VAR in data assimilation. So the use of VAR could cause additional confusion with that term. There is a third VAR which is used in this context. So just additional warning for that is probably perfect.
Yes. Yes.
There are only so many three-letter acronyms.
So the bar model describes the evolution of a set of k variables. In the context of econometrics, this kind of variables I call endogenous. Endogenous means that they are the dependent variables, in other words, over the same sample period as a linear function of only their past evolution. So the main equation of the bar methodology is like the blue one that I'm showing you. So because of the nature of the multivariate thing, this is a vector. So I'm just showing you one of the equations because the other ones are really the same thing. So the C here is an intercept, and obviously it's a vector of constant of k by 1. The alphas are a matrix of k by k. The ET here is the vector of error terms of k by 1. And the errors should have mean 0 and no serial correlation. That means that you have white noise. The P is the number of lags that you are considering in your model. So what is the number of lags? Is the number of periods that you are going back in the time about that variable. So another important thing here is that all the variables that you are including in your model have to be of the same order of integration. What does that exactly mean? Well, you have two cases. The first one is that all the variables are stationary, so that means that they don't have trend, and they don't have to be differentiated in order to have the stationary thing. And the other case is all the variables are not stationary. So that means that you have to take difference to the series in order to have the stationary thing. So another important here is the determination of the length, so the P. So it's a trade-off between the course of dimensionality and aggregate model. So there's not a recipe to find the correct number of periods that you are going back in time, but if you put small numbers, probably you are losing information, so that's a bad point. And if you put a very large number, you are estimating a lot of parameters there. And as you know, if you estimate a lot of parameters, probably you are, instead of losing information, you are adding information that you don't need. So this is a balance, so you need to check which things can work better for you.
Oh, just a question that is, for autoregressive modeling, there's an Aki information criterion for establishing order, and so you're saying there's no generalization of that to the vector case. Although you might call this vector rather than bar to differentiate from the other bar. Anyway, I'm interested if there's a generalization of the AIC for.
Yes. Another thing is how do you estimate the parameters in a bar model? Well, it's very easy because you can use the ordinary least square, so you don't have any trouble in finding the parameters of that. And the only thing that you need to do is to determine the endogenous variables, I mean the dependent variables that you are using in your model. And the beauty of this type of model, of this type of approach, is instead of the estimation, is the interpretation of this model, because the bar methodology allows interpretation about the dynamic relationship between the indicated variables through the granular causality. This is an important thing, because other type of models don't give you the chance to interpret the causality of the variables that you are using. So I think honestly that this is the beauty of this type of approach, because you can find the causality between variables, and that's an important issue. So what type of time series data are we using? Well, the data that we are using in this problem are taken from the National Geophysical Data Center and the National Climatic Data Center. And as you know, we are using data for the sun and for the terrestrial climate. For the sun, we are taking the sunspots number and the total solar irradiance, and another proxy variable is an isotope that you find in the ice cores of Greenland, for example. I choose the beryllium-10. You can also use another type of proxy variables, but it seems that this isotope is the most stable and gives you more information about the variations of the solar activity and the climate.
The last feature, why is this only until 1985? Are there no recent data points?
No, let me explain that point. That's important. So let me explain that point. So I'm showing you the availability of the data of each variable, and the period of the study should be the same. You cannot mix scales of data because you can get not trustable results. So you should be careful about the period of study that you are employing in your model. So I'm going back in time, even if you have the beryllium concentration measure from this period of time and this kind of stuff. So most of the time series, for example, the total solar irradiance, I will explain that point later.
How did you get that back to 1610?
Yes, that's a big point. Yes, also for example, the sunspot don't have any trouble because you can find measures from the 1600s, so you don't have any trouble with that. But the problem is with the Maunder minimum, because there's no way to interpolate data here. So I avoid that point, so that's why I started from this and beyond that. So probably the sunspots are the most remarkable feature of the solar activity. You have those type of measurements, the sunspots number and the groups of spots number, so we don't have trouble with that. But what about the total solar irradiance? So the problem with this variable is we have really good observations through the satellites from the 1978. So how can we go back to that time, to the 1600s? So we didn't do that. So we look for information in the literature about that. So other groups try to reconstruct the series taking into account another proxy variable. So yes, I know that's not a good point, because it depends on the type of analysis that you are doing to go back in time. So there's no way, because sometimes you need to go back more years than you expected in order to have more data and that kind of stuff. But this is a problem with this type of variable, for example, because we are taking the data from another person who took another proxy variables in order to go back in time. So that's a problem here. So that's the point. So from 1750 to 1978, we are taking the values from the reconstruction time series by Lin. So this person is taking another variables, another proxy variables. In fact, she's taking the, I think that the isotope records for that, and she's going back with this type of stuff. So what about the isotopes? They are produced with cosmic rays when the cosmic rays collide with atmospheric molecules in the upper atmosphere at high speeds, and the products of that interaction are deposited in ice cores, and somehow people in Greenland go and drill the surface there and get samples of ice, and that's just an example of how the layers look like. So in that way they are dating. This is a geological dating of that kind of isotope. So what about the terrestrial climate? So well, we are focused our attention at the moment in major climate phenomena. So we try to choose the best variable that can model the climate phenomena at the micro scale. So we choose the global temperature in both hemispheres. Why in both hemispheres? Because it seems that they have a type of correlation between the temperature that you can measure from the northern part and the southern part. So that's why we are using both. We also are using the MAE, the Multivariate ENSO Index, the Northern Atlantic Oscillation Index, and finally the Pacific Decalage Oscillation. So in that way, we are choosing the best variable we think in order to model the climate, the terrestrial climate at the micro scale, and the period of time is that.
One question. Is there any particular reason why you have periods of, like for the solar data, you have from 1600 to 1885, and then for the climate data, you have a different period of study? So you don't match the periods?
No, okay, let me explain that point. If you, yes, you need to match the periods of time. If you are, for example, I will show you later that I'm doing two bars models, one devoted to the solar activity and the other one that involves the solar activity and the terrestrial climate. So if you are mixing the solar activity and the terrestrial climate, obviously you need to match the periods of time, because otherwise you are introducing some type of bias, and this is a disaster. That yes, that's a good point. So I won't enter into details here, but I just want to mention that the temperature, for example, shows an structural change here in 1977. So the multivariate ENSO index, it's an average of other parameters. And you also have a breakpoint here in that time, in 1977. The now doesn't show that kind of stuff, but this kind of variable was chosen because it involves certain patterns in the northern part of the planet, so they are totally different. And the PDO also shows two breakpoints in the time series data, so we have to model this kind of breakpoints somehow in the model. So how can we apply the bar methodology to that? Well, as I mentioned before, in order to apply the bar methodology, you need the time series to be stationary. So I already give you the recipe for that. So in the case of the breakpoints that you also observe in the time series, you need to introduce them as a dummy variables. So in this case, we have 3 dummy variables. And the independent variables here are the number of sunspots, the TCI, and the other variables, the dummy variables here. The period of study of this model is between 1950 and 2008. So the number of lags in this model was chosen to 4, and obviously the bar 4 model is for 5 equations. So they look awful in the sense that you have to compute a lot of parameters here, but I just want to mention that it's really easy to compute because you only apply the ordinary least squares for that. So I'm just want to show you that you have, in reality, for this model, you have 5 equations. Each one describes each parameter. And obviously, when you compute and estimate the parameters in that model, you need to give the statistical validation of that. So the most important thing in the statistical validation is that because of the Granger causality, it seems that the solar activity through the measurements of the irradiation doesn't affect the major climate phenomena represented by these variables. So we are arising to another conclusion that the people usually give, that there's a good correlation of that. We are not finding that. And about the solar activity, I just want to mention that we found this type of model, the same thing, but with 8 lags. And summary and future work is that the wavelet analysis of the time series data can give misleading periodicity, so you should be careful in applying this kind of techniques in this type of data. So we propose a model based on the Barr methodology. In the first part, we model the solar activity and the solar terrestrial connection, and the other part is just devoted to the solar activity. For the solar activity, we found that apparently the beryllium, that kind of isotope, doesn't play a fundamental role in the solar activity. So that means that it's probably it's not a good proxy to study the solar activity. So we can remove that variable from the model, and it doesn't matter. And the big conclusion here is because of the solar and terrestrial connection, it seems that the solar activity has a wake connection to Earth, at least for the major climate phenomena that we consider in this work. So some ideas for the future work. The first is that we need to search for another proxy variables that describe the solar activity better. And why? Because we need to improve the Barr model for interpretation. We need to analyze the solar data by cycles and not the time series as a whole. And we need to improve the technique to estimate the structural breaks in the temperature data, the May and the PDO, because that kind of points are really, really important. And because of that, we need to introduce variables related to regional climate in order to obtain a Barr regional model in order to a global one. And we need to solve the multi-scale and reconstruction problems in some of our time series. So that's the thing that I want to talk about. So thank you very much.
What about the other sunspot minimums that are correlated with reduced temperature, the cold climates, the Dalton minimum and the spotter minimum?
Excuse me?
There are other solar spot minimums that are correlated with low temperatures on Earth. Can you have other explanations for them, the same way you had possible volcanic explanations for the Warner minimum?
I don't have at the moment, I don't remember that, but other people think that it's not a scientific explanation of that. They only say that probably it's because you don't have observation and that's all.
The other thing is, color solar radiance is not necessarily the issue. It's the change in the radiance as it switches from more ultraviolet to more infrared throughout the cycle, which may be important.
Mm-hmm. Yes, maybe, but yes.
So there's an important person called Lockwood that made a strong statement about 10, 15 years ago, showing that there is no correlation between the global temperature and the solar variation. But recently he showed that, for example, England, there the regional temperature and the solar variation is actually quite strong. So then it comes in that regionally it can have a big impact. And then about the moderate minimum, there is actually quite strong historical studies that the sun was very intensely studied during the modern various reefs and mass reefs, and they basically say that a lot of solar phenomena like flares and so forth was studied. And when someone found a sunspot, it was very prestigious to find a sunspot. So it is not the argument that it wasn't well studied. It was extensively studied, and there were no sunspot identified. So I don't think it is a strong support for the claim that the sun wasn't well studied because of cloud or something else during the modern.
Yes, of course. Yes, in the future we need to include that kind of variables about the clouds and that kind of stuff. But we don't try to model the climate Earth as a whole. We are just trying to understand the possible relation among the variables that describe the solar activity and the terrestrial climate, because many people are still claiming that there's a high correlation because of that. But maybe the works that are talking about that is because they are getting correlation very high, but they don't analyze the time series in that way. They are using the wavelets method, and the statistician told me that the wavelet methods in that sense can give you misleading results, because you are somehow altering the time series somehow, and they are giving frequencies that you need to understand that. So yes, so that's why.
I don't know if there is any meaning for the breakpoints. So you have a time series, and then you take the trend out and you look at the breakpoints.
Mm-hmm.
So sunspots, total solar irradiance, and the beryllium, do they show the same breakpoints?
No. Well, supposedly.
Does it have anything to do with the dynamics?
No. Supposedly the breakpoints could be associated to the man intervention because of that, but we are not pretty sure about that. So that's why in the extra ideas for the future work, we are thinking about how to calculate the breakpoints, if they are really exist or not.
And maybe also it would be nice to look at the cloud cover and then relate that with.
Exactly. Yes. Yes. Thank you.